Today we're going to study Boyle's Law and Charles' Law. I'll be using pages 4 and 5 in your notes. Now, Boyle's Law discusses pressure and volume, and it is going to be the volume of a fixed mass of gas varies inversely with the pressure. So if the volume goes up, if volume increases, the pressure will decrease. That's simply how it is going to work. Now, there's a memory trick for remembering which that Boyle's law has to do with pressure and volume. And remember that we boil, like boil, B-O-I-L, right? We boil peas and vegetables. Okay, if you remember that little click right there, it helps to remember P and V, right? Okay, so now what this is really assuming too is that the temperature remains constant. So temperature is the same on its initial condition and its final condition. So since it's constant, it's not really excluded. So I really just I scratched it out right here, but it's really T1 equals T2. So let's do an example. Example number 3 says a gas has a volume of 7.4 liters at 765 millimeters of mercury and 25 degrees Celsius. What volume in liters will the gas occupy if the pressure is increased to 1075 millimeters of mercury and the temperature remains constant? So since I said temperature remains constant, I really don't need to use it. I can pretty much kind of cross it out. Now, this is going to start to flex your algebra skills, and it's actually really easy if you follow the formula that I'm going to give you. We have P1 equals V1, P1 V1 equals P2 V2. What this is doing is it's going to give us an initial condition and a final condition. All right, and almost all of these problems are starting with an initial condition and comparing it to a final. What is essential is that you glean the information from the problem. So it says that it starts with the volume of 7.4 liters. Now I have these words in red. You'll have to write them down yourself, but they're really helpful. If you say that your initial volume was 7.4 liters and my initial pressure was 765 millimeters of mercury, it asks me the volume in liters, so I'm going to call that X. That's my unknown. And my final pressure is 1075 millimeters of mercury. Okay, so now I need to take what I've written in my from my known information and plug it into the equation and then just solve for X. So what I am going to do is I'm going to take P1 is going to be 765, and hold on, I'm going to put my units right here, millimeters of mercury. I'm going to put my units underneath so I have enough space. And I'm going to multiply by my V1, which is 7.4, and my unit is liters here. And then I'm going to equals my pressure, which is going to be 1075 millimeters of mercury, and I'm going to substitute X in there. Now notice that the units don't change. So millimeters of mercury on both sides of equation. Just like algebra, if you have something on that's the same on both sides, you can cancel it out. And my final unit for my X is still going to be liters because it's liters on the left side. So I'm going to actually erase these units because they're getting in my way. So what you should do is just divide both sides by 1075 so that I can isolate X. By doing this, I cancel out 1075 on the right side. So all you have to do is type in your calculator 765 times 7.4 divided by 1075. And my final answer is going to be 5.27 liters. And we'll go down to example number 4. This is going to be exactly the same kind of way. A gas with an original volume of 1.5 liters, 1.50 liters, is expanded to a new volume of 4.75 liters and a new pressure of 2.20 atmospheres. So in this case, P1 is my unknown variable. Okay. Sometimes the unknown variable moves around and it goes all over the place. Now calculate the original pressure of the gas if the temperature of the gas was held constant during the expansion. So temperature again is constant, so we can exclude it. So in this equation, it would be x times 1.5, and I'm going to exclude units just for space, okay? And 2.20 times 4.75, okay? And now if one side divide both sides by 1.50 to isolate x, I will now end up with my x value is going to be 697 atmospheres, and that's my final answer. Okay, so these problems are actually pretty quick. As long as you glean the correct information and set your x value. Setting your x value is imperative. Oh, and I made a mistake. Hey, that is supposed to be x atmospheres. I'm sorry, guys. All right. One other thing I forgot to point out is that I have liters right here and liters right here. So since the liters are the same, that's why you can drop those units. You just need to make sure you have the same units on both sides, and it's no big deal. Okay. If you don't, you need to make sure you convert units like we've done before. All right. Now, it says we now need to be able to take this into the theoretical level by connecting Boyle's law to the kinetic molecular theory. So, why does an increase in volume lead to a decrease in pressure? Justify your answer in terms of kinetic molecular theory. Well, as I increase the volume, I'm going to increase the shape of my container. And this will increase the amount of empty space that is available. What that does is, since there's more empty space and there's more surface area, I will reduce the number of collisions with the container. Less number of collisions will lower the pressure. This is what Boyle's law looks like when you look at it on a graph. So as you can tell, it does not, on the left side, if I plot pressure, volume versus pressure, y versus x, that will give us a curved line, and that does make sense. If you've ever tried it, if you ever tried squeezing a bottle that's full of just air, you notice that it gets really, really, really hard to reduce that volume once you get to a certain point, and eventually you reach this kind of asymptote right here. That's because you're actually contracting the actual molecules now, and you've kind of started to run out of empty space. Now, the interesting thing is that just because of a cool little math trick, if I plot the x-axis as 1 over p, or inverse of p, I will get a straight line. All right, and this is why we call this an inverse relationship. Okay, this is the only one that is an inverse relationship. The rest of them are all direct relationships. So this is a cool little trick to know before you go to AP or IB chemistry. Charles' law is a mathematical relationship between volume and temperature. Now, if volume increases, then that means temperature will increase. That means that it says that the volume of a fixed mass of gas varies directly with the Kelvin temperature. Okay, so I must say right now that the temp must, all right, must be in Kelvin. All right, there is no trick, there is no shortcut for this. It must be in Kelvin. because Kelvin is an absolute zero and you cannot have a negative Kelvin. If you use Celsius, you will end up getting negative numbers and it won't work right. Now, the memory trick for this is Charlie Brown's Thanksgiving is on TV. Okay? So you get it, temperature and volume, and it says it's Charlie. Okay? Hopefully that will help you remember that for your test. So let's go ahead and do some examples. Again, just like Boyle's Law, we're just going to glean information from the problem, write down known information where the red letters are. So a sample of gas has a volume of 150 milliliters when its temperature is 17 degrees Celsius. Okay, so we got to figure out what that is in Kelvin first off. So it says 17 degrees Celsius. If you add 273, just do a quick addition, we will end up with 290 Kelvin. Okay, so I should write down 290 Kelvin. If the temperature is increased to 32 degrees Celsius, so take 32 degrees Celsius and then add 273, I will end up with 305 Kelvin. So write 305 Kelvin. Now my unknown is my volume. So, and this is going to be in milliliters. How did you know that? Because I started off with milliliters for V1. Okay, so the units are still going to be the same. Now, when I do the math, I'm going to use this equation, V1 over T1 equals V2 over T2. So I'm going to take 150, I'm going to drop units, divided by 290. Let's go ahead and add the units just for fun. Okay, equals X number of milliliters divided by 305 Kelvin. You're going to have to multiply both sides by 305. Okay, so algebraically you'd have to do that. So since I multiply both sides by 305, the 305 is going to be cancel out over here. The kelvins will cancel out. And so my math is going to be 305 times 150 divided by 290. That is going to give me 158 milliliters, but that's not the best answer since I have two sig figs in all of my problems. I should approximate it to 160 milliliters. Okay, so remember those sig figs, those are still important. Example number 6 says a balloon is filled with gas at 250 degrees Celsius. Now that is actually 298 Kelvin to a volume of 5 liters. What temperature in Celsius would the gas have to be changed to in order to cause the volume to drop to 2 liters? So we have 2 liters, and it asks for the temperature. Now I'm going to have to find it in Kelvin first before I change it to Celsius, because I need my units to stay the same. So I need to take 5 divided by 298 equals 2 divided by x. Now, the tricky part about this is that you have an x in our denominator, and that is actually kind of hard to isolate if you don't know the trick. The easiest trick to do is to just flip both sides, all right? So take this side and just flip both of them, all right? You're going to take the inverse of both sides, which you're allowed to do as long as you do it to both sides. That needs to be 298 divided by 5.00 and make this x over 2.00. Once I've done that, that is a lot easier to manipulate. What I need to do is I need to multiply both sides by 2. And I'm writing in green so it shows up on that red balloon. When I do that, the 2's cancel out, and I end up with x by itself. So now my calculation is going to be 2, 2 times 298 divided by 5. 5, that's a 5. All right, and that equals x. So x is going to equal 119 Kelvin. Now, that doesn't get us all the way because I asked for Celsius. So what you'll have to do is you'll have to take it and you'll have to subtract by 273. So what I do is I have to take 119 Kelvin and I need to subtract by 273, and I will get negative 154 degrees Celsius. So that is what I have to do for my final answer. If you need to know that cool little equation, just know that the degrees Celsius, whatever x degrees Celsius plus 273 will equal your Kelvin, your value of Kelvin. Okay, I'm going to erase this junk and then we're going to talk about the theory. So now, 3, 2, 1. So to connect the Charles' law to kinetic molecular theory, we need to understand, why does an increase in temperature lead to an increase in volume? Well, if I increase the temperature, it causes an increase in kinetic energy and the speed of the molecules. This causes more collisions with the container, which will increase the volume if the pressure remains constant. Those little gas particles are pushing on the container, and if the pressure has to remain constant, I need to expand the volume. Think of something more like a piston. If I increase the temperature, I will increase the volume.